This is Advent of Code 2020, day 17. The problem is called Conway cubes. And we are looking at part 1. The elves have reached out to us from the North Pole during our current flight, and they need some help figuring out what's going on with their this satellite that they have, this super secret imaging satellite. They need our help looking at the Conway cubes that give energy to the satellite, I guess. It's an experimental energy source. It is an infinite three-dimensional grid of cubes that are either active or inactive. So basically what we're dealing with here is a modified version of Conway's Game of Life, except instead of working from a 2D grid, we're going to be working with a 3D grid. So we're going to have to work with three-dimensional coordinates, x, y, z. Let's see. So the rules follow that if a cube is active, then it's 26 of its 26 neighbors. If exactly 2 or 3 of those neighbors are also active, then it will remain active. Otherwise, it will become inactive. And then if the cube is inactive, then if exactly 3 of its 26 neighbors are active, then the cube becomes active. Otherwise, it remains inactive. So, yeah, because we're working on a three-dimensional grid, if a cube is at like 1, 2, 3, that's sort of its own cube position. There are going to be 26 neighbors, 26 cubes around that position. 3 times 3 times 3 is 27. So this is the 27th, and then the other 26 are the neighbors. That's how I'm thinking about it. We will always start with a sort of a planar, if that's a word, a planar slice. That'll look like this. So a dot would be an inactive cube, a hash would be an active cube, so on and so forth. And so you could imagine this is a 3 by 3 by 1 region. And so our starting input will look something like this, although I imagine it'll be bigger. And it's from there that we want to run 6 cycles of this set of rules against the 3D space, this sort of infinite 3D space. And at the end, so this is an example of like the z-index and what the plane looks like at each of those for several ticks, but I'm just going to scroll past this because what we want to do is after 6 full cycles, we would like to see where the boot process has left us in terms of number of cubes in the active state. So for that 3 by 3 by 1 grid, we would have 112 active cubes after 6 full cycles. So we'll start there, see if we can get to 112, and then we'll jump over to the puzzle input and see where that leaves us. Okay. So let's grab this as our sample. So we will put that in sample.txt like that, save that, and we will open up part1.ruby. I think this problem lends itself well to Ruby because I am imagining keeping track of this grid of the 3D grid, this 3D space of cubes. I'm imagining keeping track of it by having an active, I can type it, an active cubes hash, which will look like, rough start there. So I have an active cubes hash, and the way I'm imagining that will look is that each time we encounter an active cube, either when we're reading in our initial input or as we're generating a new cycle, we will have a key that looks like an XYZ coordinate, so 1, 2, 3 maybe. and that will point to yeah, now I'm not sure what the value would be. I guess true, because it's active. And then if a key is not in this hash, then we would get nil back, and so we would assume that it is inactive. Yeah, I like this for like the convenience of lookup, because we can just pass in something like that to our active cubes, and we immediately either get back true or nil. Now I'm typing it out, it does look a little wonky that we're just using something like true as the value, but I think the hash itself is going to make for a more elegant solution. So I'm going to stick with this for now. This is just an example, so I'll comment that out. And then first and foremost, we need to read in our file, which for now is going to be sample.txt. And we will first split that apart by lines. So we'll split on new lines, and then getting some weird, oh, there we go. I don't know why that was formatting like that. So we'll split on new lines, and then we will map those over to split on, oh boy, so for each line, I want line.split and split on an empty string, and that will give us a 2D array of the positions. And so I think that's good enough to start. Initial plane, I guess, is what we'll call this. And so then we'll need to process the initial plane into starting values in the active cubes hash. And once we have that, we can start calling, something like 6.times do, and we'll say like tick active cubes, something like that. And that'll produce a new set of active cubes, which we will call active cubes. So we'll do that 6 times, and then we'll say, I guess, active cubes dot to a dot size. That'll be our answer. So yeah, that's going to be real easy to count then. It's just the size of the active cubes. And so we just need something called tick, which will take active cubes and will produce a new set of active cubes. Yeah, I think this is a good skeleton for what we need to do. But yeah, let's jump back here and do this piece. So initial plane dot each, and I guess active cubes is going to have to go up here. So initial plane dot each do character, and so if the next if character equals equals a dot, and I guess we're going to need an each with index here, and skipped ahead a little bit. This is going to be a row, and then row dot each with index is going to be the character with a y. This is going to be a row with an x. Those are our indices that we get with each with index. And then we have, I guess, just an assumed z of 1 because we're just assuming we're on a plane of 1. Really, we could make z be, that. It doesn't really matter because we're just kind of giving ourselves a starting position and we'll simulate it from anywhere. So then, yeah, what we'll return here, or not return, but rather what we'll inject into active cubes is this position, which will be x, y, and assumed z. Or rather, that's our key, so that key will get assigned to true for lack of a better idea for a value there. Yeah, I'm just gonna leave this at 10,000 because I think that's interesting. I'll leave that comment here. Awesome. Well, let me pry in here because I'm interested to see how active cubes looks at this point. And just to remind myself, there should be 1, 2, 3, 4, 5 active cubes. And no errors so far. So active cubes is empty here, which is not what I was expecting. What is initial plane? Yeah, I like the way that looks. I'm gonna have to X out of here to see more context. So next if, I have an assignment here instead of a comparison. That would be the issue. Let's try that one more time. Active cubes. Dot size is 5. Okay. Yeah, that looks good. So then the other thing we're going to need to do now that this is initialized is once we're doing the tick, we're going to have to be able to figure out who are the 26 neighbors. And I kind of want to save myself a little bit of typing there because I'm sure I could, basically type out like -1, 0, 0, +1, 0, 0, and so on and so forth. But I don't want to do that, so I'm wondering if I can sort of programmatically generate that real quick. So I'm thinking of something we did in one of the other solutions where we generated sort of all permutations of 3 things using some kind of like, like string, number to string kind of trickery. So if I say 26 down to 0, that's going to give us this this list of all numbers 26 to 0. And so if I then map that, so value, I guess, if we say value.toString3, this is going to give us this set of all 26 strings, all 26 of those numbers represented as sort of strings that are either, 0, 1, or 2 in each of them. Ultimately, I want the 2 to be represented by a -1 because that's kind of what each permutation will be if we're to sort of translate the current position to all of its neighboring positions. So we can take this a bit further by doing like an rjustify, because most of these are not actually, or not most of them, but some of these are missing characters that they need. So I'll rjustify that up to 3 with 0 as the padding. So that's looking better. And then we can go a bit further and split this. And so now we have all of these positional. And I think after we split those, we can map those over to I as well. Yeah, that's looking pretty good. And that gives me enough here, so I can copy that. I didn't have to do it by hand. And I can say something like neighbor chords, something like that. I'll just paste those. I didn't like how that pasted, so I'm going to say set paste. That's a little better. Okay, and what I'm going to do is replace all of the 2's with -1's. Cool. And then the only thing we don't care about is 0, 0, 0, because if we were to translate our current position by 0, 0, 0, that just is our current position. That's our 27th option, not the one we care about. Cool, so these neighbor coordinates are what we can use to translate and find all of the neighbor positions as we're doing the tick. Okay. So for the tick, we will, I guess say for all active cubes dot keys do, and that's going to be current cube chord. Oops. Oh, I'm still on set paste mode, that's why. Okay. So we're going to iterate over all of our active cubes, and we're going to get just the key part, which is going to be the coordinate that we care about. And so we will say, I guess, count of active neighbors is like something we want to run using the current cube coordinate. And if that is, well, let's check our rules now. So these are our rules. Oops. Okay. So if the cube is active, that's what we're working on. If the cube is inactive, that's a different matter and is potentially going to be a little more tricky. How do we find the positions that are going to be... So we're working with an infinite grid, so how do we sort of reasonably look at all the positions that might be in the vicinity of three active cubes? Yeah, I guess we'll have to use this same approach. Maybe sort of naively we can say, like, well, given an active cube, which is what's coming through here, given an active cube, give me all of the neighbors, and then we can check all of those neighbors to see if they need to then become active. I think that's good enough, because anything that's not directly next to a current cube is not going to be impacted by this rule. So even though there's going to be some overlap in the checking there, I think that'll still work. We could even add an optimization at some point to sort of keep track of the inactive neighbors that we've looked at so that we don't double check them. Okay, I think that's going to work. Let's just start here though, and we'll get to the inactive stuff next. Yeah, maybe we keep track of something like inactives to check, and that can be a similar kind of hash of values, and as we're doing these, we can populate that. Next, active cubes. That's something we're going to be building up as we go, and so ultimately we'll return next active cubes as our answer. Yeah, so I'm going to put this here because I think this is what we'll do as the second step of the tick. So yeah, something like inactives to check dot keys dot each do something like that. And I'm realizing I'm missing my each here. Okay. Awesome. I think we're in a better position now. So if count of active neighbors, yeah, maybe we'll just say count gets this if count equals 2 or count equals 3, then it remains active. Otherwise, it becomes inactive. So the otherwise, we're just going to like ignore it. So next active cubes gets cur cube chord gets true. Okay. Yeah, maybe we want neighbors gets compute neighbor chords, and that's going to take current cube coordinate, and so then we can pass that in here, current cube coordinate neighbors. Yeah. Active cubes neighbors. I think that's all going to be needed there. This is good enough here. And so then after we go through all of these, then we can take all of the neighbors and stick them into the inactives to check. So neighbors dot each do chord. I'll say inactives to check chord gets true. Okay, so what's nice about also using a hash here is that we can basically build up this list of inactive coordinates that we need to check, and we'll sort of filter out duplicates as we go so that when we get down here, we're checking like a minimal list. Great. What's it complaining about here? Avoid comparing. Oh yeah, that's a good suggestion. Does 2 or 3 include count? I like that. Okay. Yeah, I'm just trying to think if there's anything else we need to do for this first part. Oh, well, I guess we need to implement these methods. So compute neighbor chords. Maybe this we can just put in the context of this method here. Let me jump back up to the top here, and we have our current coordinate coming in. Jump back down to the bottom. And so, yeah, we'll map over neighbor chords. And for each of these, we'll want to return, I guess, nx, ny, and z gets neighbor, and then x, y, z gets chord. And so, yeah, if this is 0 and this is -1, then, yeah, we want to add them all together. So 0 would then become -1. So we just want to do straight addition with these things. So we'll say we return x plus nx, y plus ny, z plus nz. And we'll do that for every single neighbor, and that gives us, or every single kind of like neighbor translation is what these are. And that gives us the actual neighbors of the incoming coordinate. Neighbor chords. Yeah, it's kind of a misleading title, so I'll just put a translation triples for neighbors of a chord. Something like that. Okay. So that handles computing our neighbors. Then count of active neighbors. Okay. Count of active neighbors. That gets a coordinate, the active cubes, and then the neighbor chords. Neighbors, I like that. Okay. So, yeah, what do we want to do? I think we want to go through each of our neighbors, see if it's inactive cubes. I guess we don't care about chord at this point because we've already computed what we're looking for. Okay, so we might have to toss that first argument out. So say neighbors dot count. I think count can take a block like this. So we'll get our neighbor chord, and we'll say, I guess, active cubes neighbor chord. If we're able to look that up, that'll either look up true or it'll be nil, and I think the count will then just count them, and that'll be our return. Okay, so yeah, let's ditch that first argument. We will ditch it down here as well. That'll produce our count, and we'll be on our way. Okay. So I think we're going to be able to reuse some of this for figuring out the inactive check. So yeah, similarly, neighbors count Current cube chord, okay. Then we use that to count the active neighbors, and if a cube is inactive, and these are all inactive cubes, but exactly 3 of its neighbors are active, the cube becomes active. Okay, so if count equals 3, then we just add this to next active cubes. Awesome. And I don't think we have to do anything else. Otherwise, it remains inactive. The sort of stuff we did here only mattered because it was what led to this. So that's all the pieces of that. I think we might be looking at a solution here. Too many lines. That's okay. You'll have to deal with it, RuboCop. So if we run Ruby part 1, we get 112. That is really promising. Well, let's take a look at the puzzle input. Oh, that's not too big. Cool. So we'll say input.txt gets that. We'll jump back over here and change out the file that we're reading into input. Give this another run. 255. Is that our answer? It is. All right, we got a gold star doing a little 3D Conway's Game of Life. That was a lot of fun. I'm excited for part 2, so definitely check in on that video coming up next.